whenever we operate for such a short period of time, we don't use up much of the reactivity value of the fuel in the reactor. And it turns out the fuel lifetime in the treat reactor is limited by the amount of oxide that builds up on the zircaloy cladding. And we've used only about 5% or less of the fuel's lifetime based on the oxide thickness on the cladding. So as long as we continue to operate it the way we do, we won't challenge or hurt the treat fuel. And also it means that our treat reactor itself is safe, and we're not going to do anything to it that's going to release fission products up into the air, right? So that's what you always worry about with a nuclear reactor, is that you want to be sure that you've designed it and you operate it such that you'll never release any fission products or any radionuclides up into the air. The other thing we do with the treat reactor then is we make sure that whatever experiment we put inside the reactor is very safe. And we do that by doing analyses, making sure that however much energy we're going to inject into the thing is exactly within bounds of what we want it to be. It allows us to study what we want to see, and we can disrupt or melt or bust up the fuel or things like that if we want to. And the reason we can do it safely is because the experiment vehicle we put it inside of is very robust. And so we can do pretty much anything we want inside that container as long as it stays in the container and as long as it doesn't hurt the reactor.
When you're building something stick-built, you're engaging hundreds of construction folks that may not directly translate their learning to site B, right? So you have a turnover, you have different people coming in and out. So every plant almost is a new project from ground up. Obviously, there's some level of learning that goes from one to the other, but in general, they're all separate projects. But when you build things in a factory, you can bank on that repeatability the way we do in, let's say, car manufacturing facilities. We have standard equipment, the same people working shifts that are building components and assembling them together and welding and inspecting and coming up with an end product. If you're doing that 20 of these a year or hundreds of these a year, then you can really lower the capital cost of the machine, which otherwise you will not be able to reduce in a regular standard stick build approach. So there's two different approaches going on. For a larger system, economies of scale kind of works for them based on power level. So if you're doubling the size of the power output of a plant, your reactor does not become double the size, right? It's maybe 40% increment or 60% increment of size. So you get that economies of scale as you grow bigger and bigger.
Right.
But on the other end of the spectrum, for microreactors, you're looking at economies of scale in production, right? So it's a whole different approach where you're trying to make the same thing, the same material, the same geometry over and over again and try to reduce cost.
Number one, it's not nuclear versus renewables. Absolutely not. It's not nuclear versus fossil with carbon capture. We need it all. We have, if you look at overall energy production and utilization right now, it's about 80% fossil fuels when you go beyond just looking at electricity. That is a huge amount of energy to replace. And so we have a long way to go. We are going to continue needing those fossil plants to some extent and adding carbon capture to those so that we can remove that CO2 source. And that CO2 can actually be an asset sometimes if we can capture it and then utilize it for different applications. So we can talk about that in a minute. But then if we're in a region that has a really good resource for wind and solar, we should use it. That's absolutely a great thing to utilize. But there's also a lot of regions that don't have good wind and solar resources. And just because we incentivize, for example, solar in some regions, it has a really poor efficiency of production. And so we really should be pushing for that. And wind and solar, like I said, if they're there, great. Hydro, if it's available in a region, great. But we also have to think about footprint. How much land area is being taken by these resources? Do we have to clear land for that? Is it taking out farmland? Is it taking out forests? Is this an island nation that simply doesn't have enough land to consider putting in solar? So we have to keep that as a factor as well. Any good engineer knows that you get higher efficiency as you go higher in temperature. And so a lot of the advanced reactors do operate at those higher temperatures. We can take a 300 degrees C outlet steam source and boost that temperature using chemical heat pumps, mechanical heat pumps, a lot of ways that we can get to higher temperatures. But if that reactor is already putting something out at 700 degrees C, then we've automatically earned some points on efficiency. So if we think about that scenario now, and we say, okay, we need more power in region A. Well, it's got a great solar resource, so we're going to build a solar farm. And you know what? We need dispatchable power, so we're going to bring in a small modular reactor to complement that solar source. And we're going to meet the electricity demand, but you know what? We're also going to build this industrial plant right here next to it, or maybe there's already one existing, and they need heat, they need steam, they need electricity, and maybe they need hydrogen. So we can design that in a way that we most efficiently use that energy and have that return on investment in a much better condition for that owner and operator. Now, you might have lots of owners and operators in that energy park scenario.
Yeah.
But they then would work together to maximize revenues back to each of those plants while maintaining a cost-effective product for the customer.